In this problem, a 50 kilogram crate starts from rest and achieves a velocity of v equals to 4 meters per second when it travels a distance of 5 meters to the byte. We're asked to determine the magnitude of force P acting on the crate, and we're given the coefficient of kinetic friction, which is mu k equals to 0.3. So you might already notice that we're actually dealing with friction in this problem. So I'll give you a couple of minutes to try to solve it, and whenever you're ready to check the solution, simply continue the video. So step 1, obviously we need to write down what we know. M is equal to 50 kilograms. The velocity, the initial velocity is equal to 0 since it's starting from rest. The final velocity is equal to 4 meters per second, and that's at a distance s equals to 5 meters. We have mu k equals to 0.3. And so given all that, we're asked to find the force P acting on the crate. So what can we conclude from that? First, obviously from the image, we know that we're dealing with a two-dimensional problem. Given mu k, we know that we need to include friction. So friction is involved. And we're asked to find the force. And looking back at what we're given, the final state, we're given V and S. And we're asked to find P. So if one needs to write down the different steps one needs to perform, we have V, which is the final velocity. Obviously, to get the force, we need to move through A first. Once we have A, we can calculate the different forces and get P using the kinetics. So there's, again, two steps one needs to apply. From the previous video, we've seen that we started with the force, then got the acceleration to finally get the velocity. Here we're actually working backwards. We are given the velocity. We can get the acceleration using the kinematics equations. Then we can move to the force and P using the kinetics. And so we'll actually do that. But first we need to follow the steps. So step 2 involves drawing the free body diagram of the crate. So let us do that. A crate is represented by the rectangle. We know that it's subject to its own weight, mcg. Since it's lying on the ground, it would have a reaction force, nc. We know that we're applying a force P. And since we're given mu k, which is the coefficient of friction, we know that we have friction. Remember, friction always acts to oppose motion. So if the crate is to move to the right, the friction needs to push to the left. And so we mark that with Fc is equal to mu k nc. It is always good practice to start from the beginning with a reference sign convention. So here I have decided to take the positive direction to be on the right for the x-axis and upwards for the y-axis. Step 3 actually involves drawing the kinetic diagram of the crate. So let us do that. We represent the crate again with the rectangle and add the acceleration components. Since we're dealing with a two-dimensional problem, we actually have two vectors. So mcacx, which is aligned with the x-axis towards the positive direction, and mcacy aligned along the y-axis, positive direction upwards. Remember, whenever you do not know exactly where the acceleration would be, it is always good practice to take a single acceleration component on each of the axes. And remember, the acceleration component is always directed towards the positive direction. So now that we have the two diagrams, we can use the kinematics first. Remember, when we have discussed in step 1 the different steps one needs to follow, since we are given the velocity, one needs to make use of the kinematic equations first before making use of the kinetics. So we need to find A using the kinematics. One thing to note from Newton's second law is that sigma F is equal to ma. So if F is a constant, A would also be a constant. So since all forces are constant, the acceleration must also be constant. And now we can look at the different variables we have and see which kinematic equation we can actually use to find A. So looking back at what we're given the velocity and the distance, and there is no reference to time. So one cannot use any equation that involves time, since we already have a first unknown, which is acceleration. So given V and S, naturally we need to make use of the equation that involves V, S, and A, and that's the independent equation of time. So we can write that down. It's VdV equals to AdS. Performing the integration, you get the standard equation for a constant acceleration that's independent of time. We've already seen that before. V squared minus V0 squared is equal to 2a times s minus s0. Again, you can notice that the only unknown in this equation is a, so we can solve for it. S0 is equal to 0, V0 is equal to 0, S is equal to 5, and V final is equal to 4. Now replacing all that into the equation, we'll end up with a value for A equal to 1.60 meter per second squared. Again, we have adopted the positive direction to be towards the right. And so A is positive and towards the right as well. Now that we have the acceleration, we can make use of the kinetics. So we use the kinetics to find P. Since we're dealing with a two-dimensional problem, we need to write down 2D equations of motion, so two equations of motion. So the first one along the x-axis is sigma fx equals to max. Again, it's always a good practice to mark the positive sign convention next to the equation to avoid making mistakes. So writing down the different forces, we have the force P along the x-axis, that's P cosine 30, minus the frictional force, which is mu k and c, equals to max. The second equation along the y-axis, sigma fy is equal to may. We have the weight in the negative direction, minus mg, plus the normal reaction, which is positive, and c, plus the projection of P onto the y-axis, which is also positive, P sine 30. So now that we have the two equations, the next step is to look at the number of unknowns. In the first equations, the unknowns are P and NC. In the second equation, the unknowns are P and NC as well. So we have two unknowns and two equations. So the problem is solvable now. So solving, one has P is equal to 224 Newton and NC is equal to 378.5 Newton. So this is all about this problem. It is very similar to the previous problem. It's only kind of reversed. So we start with the kinematics first and move to the kinetics. But in general, the steps are the same. We start with what we know. We conclude a couple of things about the problem. We draw the free body diagram, the kinetic diagram, and then we need to make use of the equations. Now, using the kinetics equations before the kinematics is only dependent on what you're actually given in the problem. Here we're given the velocity and the displacement, so we need to make use of the kinematics first.